Here's a Class 2 problem for us to solve. You'll recall in another video we had a shortstop toss a ball to a second baseman. Well, the second baseman got the guy out, but now he's throwing the ball to the first baseman to try to get that guy out. After catching the ball tossed to him by the shortstop, a second baseman tags the runner, then throws the ball to first base to turn the double play. The first baseman catches the ball at the same height that it was thrown. The ball had an initial velocity of 17 meters per second and was thrown at an angle of 35 degrees above the horizontal. I can already determine that this is a Class 2 problem because Class 2 problems always have an angle but never have a starting elevation. Catches the ball at the same height. That's our clue that it's a Class 2 problem. If it had an angle but there was some either starting or ending height, then you would know it's a Class 3. This is a Class 2. So what's it ask us? It says, what is the horizontal component of the velocity just before it is caught by the first baseman, and how long was the ball in the air? Okay, you solve all of these Class 2 problems in generally the same way. Let me show it to you here quickly. Solve a Class 2 problem. First thing you need to do is determine the vertical and horizontal launch velocity. That is, this 35-degree angle takes that 17 meters per second, and some of the 17 meters per second is pointed up, some of it is pointed horizontally towards the right, let's say, and we have to determine how much that is. We'll do that here in a moment. Step 2, once you've done that, step 2 is determine the total time of flight. You'll figure out time to apogee, and then you end up, from time to apogee, you figure out time from apogee back down to starting position, which means you double the time to apogee. And then thirdly, you determine the range. You figure out how far away from starting position it lands. I have a little picture that might help some. The red line is the trajectory. The distance from where it starts to where it ends is the range. That's your last step. And then the green line here represents both the distance to apogee and the time to apogee. So I will use that picture on just about all of them. All right. First step, determine the vertical and horizontal launch velocity. Well, to do that, we need trig. It's the only place in this that we need trig, and the two formulas we need from trig are these. The starting velocity in the vertical direction is starting velocity times sine of theta. The starting velocity in the horizontal direction is starting velocity times cosine of theta. If any of those give you a little trouble, see my separate video on trigonometry. And then all we have to do is fill in the blanks with the particular numbers. So it's 17 meters per second times the sine of 35. I grab my calculator, I figure out what that is, and it works out to 9.75 meters per second. And then I do the exact same thing for the horizontal velocity. There are the particulars, and when you work it out on your calculator, you get 13.92 meters per second. When the ball is thrown, it starts traveling both horizontally and vertically at two different velocities, and that's dependent obviously upon the angle. Now, looks like we need us one of those there kinematic charts. I've given us two separate kinematic charts. Because I know how this problem turns out, I decided to do it that way. First question asked us is, what is the horizontal component of the velocity just before it is caught by the first baseman? That would be horizontal velocity later. But let's start by filling in what we know about this chart. We know, because we figured it out just a moment ago, that the starting velocity horizontally is 13.92 meters per second. So we'll put it right there. We also know, since it's horizontal, that it has no acceleration in the horizontal position. Well, based on that alone, we can determine what velocity later is. If it's 13.92 now and nothing ever happens to change it, that would be there's no acceleration, then it's going to be 13.92 later. So that is the answer to the question, to question A. That was easy. We didn't even have to fill out the entire chart. Now let's solve the second part. Let me get back in the screen here. How long was the ball in the air? Well, what we're going to do is we're going to figure out the amount of time to apogee, and then that's some number of seconds. We're going to double that. That's the number of time that it's in the air, or the amount of time that's in the air. Let me scroll down a little bit so we can get everything on the screen that we need. What do we know? Well, we figured out starting velocity a moment ago, 9.75 meters per second. And at apogee, vertical velocity is 0 meters per second. And acceleration, since the ball is going up and acceleration is pulling it down, they are in opposite directions. It is negative 10 meters per second, and I just wrote that wrong, but there it is written right. We have been asked to find time, which means we neither know nor care about displacement, which leads us to dash. So I'm going to write a copy of dash right down here. There we go. Now, we're interested in time, so we have to solve that for delta t, which that is solving it for delta t. Sorry, I made a long keystroke there a second ago. And then all we have to do is fill in the numbers and simplify, and we'll have, well, we won't have our answer, but we'll be awful close to our answer. Substituting our numbers in, we get that 0 minus 9.75 divided by minus 10. When you simplify that, it comes out to 0.975 seconds. Again, that is the time from kicking it to apogee. We have to double that to find out the total time it's in the air. When I double it, it comes up to 1.95 seconds. And that, my friends, is the answer to part B. And that wasn't so bad at all, was it?